Hello friends, welcome to the session. Continuation of chapter 1, that is measurement system. In the last session I discussed about one concept in measurement system, that is types of instruments. Now we'll see the another concept with respect to measurement system, characteristics of instrument. Yes, I told that what is the need of this characteristics of instruments is to select a instrument for particular application. Yes. First you know the characteristics of instrument. Yes. By knowing the characteristics of instrument only, then we can select an instrument for particular application. Then I told that the characteristics of instrument is analyzed under two conditions. One is static condition or slowly time varying condition. Then that characteristics are nothing but a static characteristics. Then the characteristics of instrument is also analyzed under a dynamic condition. Those characteristics are nothing but a dynamic characteristics. That means in general the characteristics of instrument is two types of characteristics. One is static characteristics of instrument. Static characteristics. We can analyze under static condition, then it is a static characteristics. The another one is dynamic characteristics of instrument. Yes, dynamic characteristics of instruments. Now we'll see what are the different types of static characteristics and dynamic characteristics we are using. Yes, isn't this? The first one is static characteristics. Yes, these are the characteristics of instrument under static condition or slowly time varying condition. These are the characteristics of instrument under static condition or slowly time varying condition. What are the different types of static characteristics? One is accuracy. Accuracy of instrument. Another one is resolution of instrument. Resolution of instrument. Third one is precision of instrument. Precision of instrument. Then fourth one is linearity. Yes, linearity of instrument. Another one is sensitivity. Sensitivity. Then another characteristic is repeatability and reproducibility. Repeatability of instrument and reproducibility of instrument. Reproducibility. Then one more characteristic is range, span. Range of instrument and span of instrument. Then eighth one is hysteresis of instrument. Yes. The ninth characteristic is dead zone, dead time and threshold. Dead zone, yes. Dead time and threshold. The 10th one is drift of instrument. One more characteristic is static error. All these are the static characteristics of instrument. But in all these characteristics, these characteristics are desirable characteristics of an instrument. Yes, desirable characteristics. That means during design of this instrument, we must design in such a way that we want these characteristics. We accept these characteristics. And these are undesirable characteristics. These are undesirable static characteristics. Undesirable static characteristics. And this is the desirable static characteristics, undesirable static characteristics. During design of instrument, we can design the instrument in such a way that we don't want these characteristics. But even though we don't expect these characteristics, after usage or practically we are getting this type of characteristics, then name is given as a hysteresis, dead zone, dead time, threshold, drift, static error, like that we are giving the names. Understood? Now I want to explain in detail about these static characteristics. But from this, the questions may be expected like this also. Which of the following is desirable static characteristics? Like that questions are asking. Which of the following is undesirable static characteristics? Like that questions are asking. You ready to answer by remembering which is desirable and which is undesirable static characteristics. Yes. With this knowledge, now we'll start with the first one is accuracy. How to define the accuracy of an instrument. Okay. Quick note down. Define what is the accuracy of an instrument. The first one is accuracy. Tell me, how to define accuracy of an instrument? Yes. For example, in the measurement of 5 volts, we are measuring 5 volts. The meter showing the reading of 4 volts. Particular meter showing the reading of 4 volts. In the measurement of 5 volts, the meter showing the reading of 3 volts. In the measurement of 5 volts, the meter showing the reading of 2 volts. Like that. Then which is more accurate? Voltmeter 1 is more accurate. Then which is less accurate instrument? Voltmeter 3 is less accurate. Then how we are telling that it is more accurate and it is less accurate? Yes, by comparison of this measured value with the true value. This is the true value, but all these are measured values. Understood? True value means the value to be measured. The expected value is nothing but the value to be measured. Yes, the expected value is nothing but a true value. For example, I am measuring 10 volts. The 10 volts is not a measured value. 10 volts is the true value or expected value. But after giving 10 volts input to the meter, whatever the reading of the meter we are getting, that is the measured value. But if you are giving some input means exactly that input you don't get in the reading of the meter. There must be some error. Then after that, whatever the reading we are getting, that is nothing but a measured value. That's why this 2 volts, 3 volts, 4 volts is measured values, but this 5 volts is true value. Then it is more accurate, it is less accurate. How we are telling? By comparison of measured value with the true value. That means how to define accuracy means it is the degree of closeness of measured value with the true value. Important. The questions are framing based on this concept, based on the definitions itself it is framing. The accuracy is defined as, resolution is defined as, like that questions are framing. That's why mainly concentrate on the definitions also. That's why one definition of accuracy, it is the degree of closeness of measured value with the true value. Yes, note down. What is the accuracy? The accuracy is defined as, yes, it is degree of closeness of measured value with the true value. It is a degree of closeness of measured value with the true value. Measured value with the true value. Okay, this is called accuracy. Yes. One more point to remember. Accuracy is specified with respect to full scale reading, or it may be specified with respect to true value. Accuracy is specified. Accuracy is specified with respect to full scale value. With respect to full scale value or with respect to true value. We can specify with respect to full scale value or with respect to true value. What do you mean by with respect to full scale value or with respect to true value means? For example, if it is given like this, a 0 to 150 volts voltmeter having accuracy of plus or minus 1% of full scale reading. This is one way to specify the accuracy. That means here we are specifying the accuracy with respect to full scale. But you also specify like this, a 0 to 100 volts voltmeter, having accuracy of plus or minus 2% in the measurement of 40 volts. Like this also specified. In the measurement of 40 volts, we don't measure exactly 40 volts. We can measure plus or minus 2% of 40 volts. That is the meaning. It is specified with respect to full scale value. It is specified with respect to true value. What is the meaning of this sentence? In the measurement of 40 volts, we don't measure exactly 40 volts. We can measure plus or minus 2% of 40 volts. Means plus or minus 2% of 40 volts means 40 plus or minus 2 by 100 into 40. How much we get? 40 plus or minus 0.8 volts we can measure. This is the meaning of accuracy. But you have the doubt here. Sir, you are telling that accuracy, again you taken as error. We don't measure exactly 40 volts. There must be some plus or minus 2% of error, like that we are telling. Yes, point to remember. Even though it is accuracy specification, but it is not accuracy, it is error. Very important. Why? Yes. If accuracy is specified with plus or minus, then it is taken as an error. You take as an error. For example, it is specified like this. A 0 to 150 volts voltmeter having accuracy of 99%, having accuracy of 40%, having accuracy of 10%, like that it is specified. Then you take directly as accuracy. If it is specified with plus or minus, then you take, even though it is accurate specification, then you take it is a error, not accuracy. If it is accuracy plus or minus 2% means, plus or minus 2% means plus or minus 2% error, then what is accuracy? It may be 98%. That is the meaning. Accuracy plus or minus 1% means plus or minus 1% is error. Then what is the exact accuracy? 99%. That is the point to remember. If the accuracy is specified with plus or minus, yes, if the accuracy is specified with plus or minus, then it is taken as an error. If the accuracy is specified with plus or minus, is specified with plus or minus, then it is taken as error. It is taken as error. That point to remember. One more point. Sometimes Instead of representing the accuracy like this plus or minus 1%, plus or minus 2%, in the problems it is represented like this. A voltmeter is having class 1 accuracy, class 2 accuracy, class 5 accuracy, like that it is given. What the class 1, class 2, class 3 accuracy means? Class 1 accuracy means plus or minus 1% of full scale reading. Class 2 accuracy means you take plus or minus 2% of full scale reading. Like that. That's why I am giving generalized formula here. What do you mean by class N accuracy? Yes. Class N accuracy means class N accuracy direct to take plus or minus n% of full scale reading. If the accuracy is specified like this class, then you take plus or minus n% of full scale reading. For example, what do you mean by class 1 accuracy? Class 1 accuracy means plus or minus 1% of full scale reading. What do you mean by class 2 accuracy? Class 2 accuracy means plus or minus 2% of full scale reading. Like that you take. This is the accuracy specification. Yes. One more point to remember with respect to accuracy. As a formula, the accuracy is defined as, yes, this is, I am defining as a percentage accuracy equal to, 100% minus percentage error. To take like this. This directly gives the percentage accuracy. Percentage accuracy equal to 100% minus percentage error. And this is with the assumption of measured value less than the true value. This formula you are giving with the assumption of measured value less than the true value. Okay. Then you also take accuracy equal to or relative accuracy. Relative accuracy equal to 1 minus, you take like this, measured value minus true value by true value. This gives the relative accuracy. This is not in terms of percentage. Not in terms of percentage. For example, this measured value minus true value by true value, I am getting 0.2. 1 minus 0.2 means 0.98 is the accuracy. In terms of percentage means into 100 you do, then you can get the percentage accuracy. This term you multiply with into 100, then we can get percentage accuracy with the assumption of measured value less than the true value. Understood? Okay. This we can define as a accuracy. Clear? 1 minus measured value minus true value by true value. Okay, this you take, this is accuracy. Okay, this is relative accuracy. But one more point to remember. Only accuracy is improved by using calibration process. Then remaining characteristics cannot be improved by using the calibration process. What do you mean by calibration? Any instrument we can do the calibration. How to do the calibration? By comparison of measured value with the true value. In order to do the calibration of instrument means the instrument which measures the true value, that is taken as a reference, that you can get the true value. Then we compare this measured value with the true value and we can adjust the mechanism in such a way that the measured value must be bring to nearer to the true value. That is nothing but a calibration. Calibration is nothing but a process of comparison of measured value with the true value and resultant is towards the true value. By using that process, only accuracy is improved, but remaining characteristics, resolution, hysteresis, resolution, linearity, all these characteristics cannot be improved. That means using calibration process, yes, calibration process, only accuracy is improved. Only accuracy is improved. But remaining characteristics you cannot improve. Okay, note down this quick. Here, this 1 minute here, you take this one is a true value minus measured value. Okay. Relative accuracy equal to 1 minus true value minus measured value by true value. That you change, please. Just small mistake that you correct that. True value minus measured value. Okay. This about the points you remember with respect to accuracy of an instrument. Okay. Okay. The next important characteristics is what is the resolution of an instrument. But simply you remember accuracy as a formula. Simply it is defined as accuracy equal to simple formula for this measured value by true value. You want percentage, like simply accuracy is defined as measured value by true value. But this is the formula with the assumption of measured value less than the true value. Okay, that point measured value by true value, that also gives the formula for accuracy. Then you define as a one more static characteristics of instrument is resolution. Write as a resolution of an instrument. How to define resolution? The resolution is also called discrimination. The another name for resolution is it is also called discrimination. Resolution is also called discrimination of instrument. Then how to define resolution? Yes, let us consider. To explain this, let us consider a 0 to 10 volts voltmeter. A 0 to 10 volts voltmeter. And the divisions are like this. This is 2 volts, 4 volts, 6 volts, 8 volts, and it is 10 volts. This is a 0 to 10 volts voltmeter having 5 divisions. 1, 2, 3, 4, 5. 5 divisions. It is again subdivided into, each division is subdivided into 5 divisions. Each division is subdivided into 5 divisions means, then you take like this. This is 1, 2, 3, 4, 5. Yes, this is 1, 2, 3, 4, 5 divisions. Again it is subdivided into 5 divisions. 1, 2, 3, 4, 5 divisions. 1, 2, 3, 4, 5 divisions. Like this we can make the, each is subdivided into 5 divisions. Okay. Let us assume that we already started the experiment. Already the pointer is at 4 volts reading. The pointer is at 4 volts reading. We already started the experiment. The pointer is at 4 volts reading. The point to remember here, this again subdivided into 5 divisions means, then what each division indicates? Each division indicates how much, you tell me? 2 by 5. This is how much? 0.4 volts. Clear? Yeah. Because this is 0, 0.4, 0.8, 1.2, 1.6, 2. Each division indicates 0.4 volts. 2.4, 2.8, 3.2, 3.6, 4. Correct? Yeah. 4.4, 4.8, 5.2, 5. Yes. 4.4. 1, 2, 3, 4, 5 divisions only. Yes. 4.4, 4.8, 5.2, 5.6, 6. Like that. Each division indicates the 0.4 volts. Yes. You already started the experiment. Let already pointer is at 4 volts reading. Now I am increasing input to 4.1 volt. Still the pointer is at 4 volts only. Now I am increasing the input to 4.2 volts. Still the pointer is at 4 volts only. Now I am increasing the input to 4.3 volts. Still the pointer is at 4 volts. Now I am increasing the input to 4.4 volts. Now meter shows the reading of 4.4 volts. Then the resolution of this voltmeter is 0.4 volts. Yes? No sir? If you increases to 4.2 or 4.3, the pointer may be slightly changes, it may be in between. But it is undesirable value. We cannot measure. What is that? That is not exact value. After 4 volts, by using this meter, what is the exact value you can measure? 4.4 only, not 4.2, not 4.3, not 4.1. We are measuring that voltage means it is not exact value. Next certainty value is 4.4 only. Understood? That's why the resolution of this voltmeter is 0.4 volts. Then how we can define the resolution? Yes, tell me. Very important definition. Yes. The smallest change in the input, the smallest change in the input that can be detected by an instrument is called resolution. For 0.1 volt change, is it instrument is detecting? No, that's why it is not a resolution. 0.2 volts it is not detecting, 0.3 is not detecting, how much voltage it is detecting, 0.4 volts is detecting, that's why resolution of this voltmeter is 0.4 volts. That's why smallest change in the input that can be detected by an instrument is called resolution. Yes, write down the definition. Definition is smallest change in the input, smallest change in the input that can be detected by an instrument is called resolution. Smallest change in the input that can be detected by an instrument is called resolution. Yes. Tell. But you have the doubt here, sir. Why you are explaining like that? Already a pointer is at 4 volts like that. Why you are explaining? Why not you explain from 0 itself? Yes. The point to remember, in general, resolution is measured from non-zero, not from 0. No doubt at all. If you measured from 0, there is some problem in some instruments, because at starting any instrument is having more inertia. Because of that inertia effect, we don't measure exact value. That's the reason why in general resolution is measured from non-zero. In general, yes, in general resolution is measured from non-zero. Measured from non-zero. In order to eliminate the effect of inertia, measured from non-zero. This point also you remember. One more point. As a formula, resolution is defined as resolution equal to full scale reading by number of divisions. Yes, full scale reading by number of divisions. That is, if number of divisions are increases, then what is the resolution? If number of divisions are increases, resolution is also increases. Don't confuse. If number of divisions are increases, resolution is also increases. Not according to mathematics, according to technically. Here don't consider the mathematics here. If number of divisions are increases, resolution is also increases. It is not mathematics. But by seeing this formula, if number of divisions are increases, resolution is reducing, like that, you don't say that statement here. If no doubt at all, mathematically that is correct, but technically it is correct. If the number of divisions are increases, resolution is also increases. For example, take this example here. When I make each division is 5 divisions, subdivided into 5 divisions, what the resolution we are getting? 0.4 volts. In the same example, if each division is subdivided into 10 divisions, if you make 10 divisions, means 2 by 10, how much resolution we can get? 0.2 volts. 0.2 volts is high resolution or 0.4 volts is high resolution? 0.2 volts is high resolution. Smallest change in the input that can be detected by an instrument is called resolution. Small value is considered as a high resolution. That's why 0.2 volts is high resolution, 0.4 volts is less resolution. If you compare these two. That's why when I'm making 10 divisions, for 10 divisions I am getting 0.2 volts resolution. For 5 divisions I am getting 0.4 resolution. 0.2 is high resolution as compared to 0.4. That's why if number of divisions are increases, what the resolution is also increases. This is the statement. That's why if number of divisions are increases, resolution is also increases, not according to mathematics. This is according to technically. Point to remember. Clear? Okay. One more point. Listen please. For example, 2 voltmeters. One is V1 voltmeter, another one is V2 voltmeter. Both are 0 to 10 volts voltmeter. This is 0 to 10 volts voltmeter and it is also 0 to 10 volts voltmeter. Both are 0 to 10 volts voltmeter. But this voltmeter, one is designed like this. This is 5, 10. Only it is designed with 2 divisions. Voltmeter 1 is designed with 2 divisions only. This 1, 2. But voltmeter 2 is designed like this. This is 0, 2, 4, 6, 8, 10. Like this it is designed. Now tell me. Not only 0, 5 and 10. From 0 to 10, any value, 1, 2, 3, 4 like that, any voltage is measured more accurately by using which voltmeter? In these 2 voltmeters, by using which voltmeter we can measure the unknown value more accurately? Voltmeter 1 or voltmeter 2? Yes, voltmeter 2. I am talking about only, I am not talking about only 0, 5 and 10. Any voltage I am taking in between 0 to 10. Then by using which voltmeter we can measure more accurately? That is by using voltmeter 2. That means, what is the observation here? If number of divisions are increases, what is the resolution? Yes, resolution is increases. If number of divisions are increases, resolution is increases. Then what is the accuracy of measurement is also? We are here, there is a more number of divisions now, we are measuring more accurately. Accuracy of measurement is increases. Yes, accuracy of measurement is also increases. Hence, resolution is one of the supporting characteristics of accuracy. Therefore, resolution is one of the supporting characteristics of accuracy. If you design the instrument with a high resolution, then that instrument will offer high accuracy. That is the meaning. One of the supporting characteristics of accuracy. Characteristics of accuracy. Okay, this point also you remember. One more point to remember with respect to resolution. By knowing the resolution of instrument, we can determine dynamic range of the instrument. Then how to write dynamic range of the instrument? Okay, the dynamic range of the instrument equal to measurement range by actual measurement range by resolution gives the dynamic range of instrument. The dynamic range of instrument equal to measurement range by resolution gives the dynamic range of instrument. This, by knowing the resolution, we can determine the dynamic range. Dynamic range we can determine. Okay. Note down. This is about what exactly resolution of an instrument, or it is also called discrimination. Clear? Note down quick. Yes. Another important characteristics of instrument is precision. Yes. Before discussing the precision, first I will discuss linearity and sensitivity of instrument. After that, we go for precision of instrument. Yes, I'm changing this sequence here. I'm discussing, first I will discuss what is the linearity of instrument. The linearity of instrument. Tell, when the particular instrument is said to be linear instrument. Here I am not talking about linear element. That you know what is the linear element means, which satisfy both superposition and homogeneity principle, then we can say that element is linear element. But here I am talking about linearity of instrument. When the particular instrument is said to be linear instrument means, yes, if the output follows the input, whatever the output we are measuring, if that output follows the input in any instrument, then we can say that that instrument is linear instrument. Or if there is a linear relation between input and output, if you draw the characteristics between input and output in any instrument, if you draw the characteristics between input and output in any instrument, if the input and output characteristics are linear, then we can say that that instrument is a linear instrument. That instrument is linear. That is, how to define linearity of instrument means, if the output follows the input, if the output follows the input, or if there is a linear relation between input and output, if there is a linear relation between input and output, then it is called linear instrument. Then it is called linear instrument. But point to remember here, linearity is not a necessary condition. It is sufficient or desirable condition only. For example, once we are designing any instrument, during the design, if linearity is possible, then you take linear. That is preferable, no doubt at all. But if linearity is not possible, don't think like this, we don't want to design that instrument. That is meaningless. That's why what I am telling here, linearity is not a necessary condition. If it is there, you select. If it is not there, then you go for non-linear instrument also. No problem. That means linearity is not a necessary condition. It is a sufficient or desirable condition only. For any instrument, linearity is not a necessary condition. Not a necessary condition. It is sufficient or desirable condition only. Desirable condition only. But why it is sufficient or desirable condition? If it is linear, what is the advantage? Yes. One of the main advantage of linear instrument is, if it is there, first preference you give the linear instrument. Why I am telling like this means, yes, in linear instrument, the scale is linear. We can design the scale is linear. If the scale is linear, what is the advantage? That I want to discuss. That means, in linear instruments, a scale is linear. Scale is linear or uniform scale. Linear scale or uniform scale. uniform scale. Then what is the advantage of linear scale or uniform scale? Linear or uniform scale? Yes. Design of scale is simple. Design of scale is simple. We can design the scale simply. Then unknown value is measured with a clarity and certainty. This is important. Unknown value is measured with a clarity and certainty. With a clarity and certainty. Okay, that is the advantage of linear scale. We can measure the unknown value with a clarity and certainty. Linear scale means uniform divisions. We can make the uniform divisions. For example, it is a 0 to 20 volts voltmeter. Then we can make the divisions like this: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This type of scale is nothing but a uniform scale. We can make the uniform divisions throughout the scale. Then this is nothing but a linear scale or uniform scale. But what about the non-linear instrument? In non-linear instrument, scale is non-linear or non-uniform. In non-linear instrument, yes. Parallel note down, scale is non-linear or non-uniform. It's a non-uniform or cramped scale. Yes, cramped scale or crowded scale. Okay, this is the problem. But what is the drawbacks with non-linear scale or non-uniform scale? Design of non-linear scale is complex. Design of scale is complex. Yes, design of scale is complex. This is one drawback. Unknown value is not measured with clarity and certainty. I think you are used MC instrument, MI instrument in the laboratory. Yes, in the use of MC instrument, whatever the unknown value is there, that unknown value is measured with clarity and certainty. But once we are using MI instrument, we cannot measure exact value. For example, in the measurement of 19 volts or 18 volts, that exact value we cannot measure. That is the problem. That's why unknown value is not measured. Unknown value is not measured with clarity and certainty. With clarity and certainty. Okay, that is a problem with the non-linear instruments. Cramped scale or crowded scale means like this. For example, if it is a 0 to 100 volts voltmeter, if it is a 0 to 100 volts voltmeter, it is a 0 to 100 volts voltmeter, then the scale will be designed like this. Let this is 15 volts, this is 40, this is let this is 25 volts, this is, then this is 30 volts, this is 55 volts, then this is 56, 57, 58, this is 70 volts, and this is 85, this is 90. Like this we can design. In lower portion of the scale, it is a crowded or cramped. It is a cramped one. In upper portion of the scale, it is enlarged. It is enlarged. But in middle portion of the scale is somewhat it is designed as a linear. It is a cramped design. In upper portion of the scale is the scale will be enlarged. We can use more values division. 70, 85, like that we can use the more values. It is a crowded design. This is expanded. Upper portion is expanded. This is expanded design. But point to remember, in non-linear scale also some portion may be linear. Then which portion of the scale is linear means the middle portion of the scale. Sir, how it is only in middle portion? Why not is upper and lower portion? That I will discuss in one of the non-linear instrument, that is in MI instrument, that I will discuss. Okay, that means point to remember, in non-linear instruments, the middle portion of the scale may be linear. But we must maintain some condition to design that portion is linear. Then which condition must be satisfied, that you will see later. In non-linear instrument, the middle portion of the scale may be linear. The middle portion of the scale may be linear. Okay. Then this about what is linear instrument and what is the non-linear instrument. But point to remember, in any instrument, due to non-linearity, the input and output characteristics are like this. This is the ideal characteristics. This is ideal characteristics of instrument, and this is output, and this is input. Then due to non-linearity, I am getting the characteristics like this. Due to non-linearity effect, this is the characteristics due to non-linearity. Characteristics due to non-linearity. Then because of non-linearity, this is the ideal character. But due to non-linearity effect, I am getting the characteristics like this. Then in this instrument, how much percentage non-linearity is present? How to calculate? Important formula. Percentage non-linearity equal to maximum deviation from ideal line. This is the maximum deviation. Yes. Maximum deviation from ideal line. By full scale reading into 100. Full scale reading into 100. Like this, you calculate percentage non-linearity. In this instrument, how much percentage non-linearity is present is calculated. Percentage non-linearity equal to maximum deviation from ideal line by full scale reading into 100. Once you know the percentage non-linearity, 100% minus percentage of non-linearity gives the percentage linearity. Clear? Okay. This is a calculation of non-linearity. If change in deviation is given and maximum value and minimum value is given, then how to calculate percentage non-linearity means we can also apply like this, change in deviation by maxima minus minima. Like that also we calculate percentage non-linearity. But here once you know the change in deviation, I don't know about maxima minimum. This is minima is 0, maxima is you take full scale value, then it is a full scale reading I taken. Understood? If any minimum value and maximum value is given, then we can substitute here maxima minus minima. That gives the percentage non-linearity. By considering maxima and minima also you can write the formula. Okay, this about what exactly linearity of an instrument. But one point to remember here, non-linearity is not desirable, it is undesirable characteristics. You don't expect that characteristics, but if the possibility is not there for linearity, then compulsory we can use linearity. No other choice. Sir, if possibility is not there for linearity, then compulsory you can use a non-linear instrument. No other choice. Understood? But non-linearity is one of the undesirable characteristics. Clear? Okay. This about what is accuracy, resolution and linearity of an instrument. In the next session, we will continue with what is sensitivity, precision and reproducibility, repeatability, all these characteristics I want to explain. Clear? Understand? Concentrate.